GCC, we're back to talk about chapter 14 some more. We're going to talk about the 4 intermolecular forces in this video. So the first one up is London dispersion forces. So I tend to call this London forces, but dispersion is also a name for this force. So keywords for London dispersion force is temporary and non-polar. So this force is very temporary, and it's between non-polar molecules or atoms that form when the two of them get very close together. So if you can imagine, I have 2 non-polar molecules here. Now, we know electrons go around the nucleus. So they're going around and around and around. And let's say for one moment, all the electrons, or most of them, are on this side of the nucleus. So that side's going to be negatively charged for a moment, meaning the other side is a little bit positively charged. And this is just temporary. So again, we're saying the electrons are kind of pushed more to one side. So for a moment in this atom, this side's a little bit negative and this side's a little bit positive. Well, what's going to happen to this other atom next to it? Because this is a little bit positive, it's going to attract the electrons over. So this side will have the electrons come over and it'll be a little negative, and then this will be a little positive. So for a moment, we have delta plus delta minus interaction between these 2 molecules. But then the electrons go back to normal and there's no attraction, and so the molecules go away. So it's very, very temporary. So usually it's seen in gases because there's not a lot of attraction. So again, they come together, there's an interaction for a moment, and then they go away. So often this is seen in gases, and that's why they're gases, is because they're not attracted. So gases, again, are when the atoms are far apart from each other with lots of empty space in between them. Now, one thing about London dispersion forces is the bigger the molecules or atoms, the more electrons you have, so the more strong the force can be. But in general, London dispersion force is the weakest force of all out of the 4. So here's just a little picture showing you what I was trying to demonstrate with my little atoms here. We have 2 molecules that are non-polar coming towards each other. For a moment, the electrons represented by the black dots go to one side. That makes that side a little bit minus because the electrons are over here. The other side is a little bit plus because the electrons are gone. This makes the other side have the electrons pulled over towards that positive charge in the first molecule. So in the second molecule, the electrons are pulled over and it makes that a little bit minus. And then the other side of it is a little bit positive because the electrons are largely gone. So for a moment, we have between the 2 molecules an attraction. See how we have a delta plus and a delta minus ends close together between the 2 molecules? The little black line represents the force. And it's a temporary force, it's a weak force, and it goes away, and then the molecules fly apart from each other, and chances are it's a gas. Here's another picture of the same thing. We start out with 2 non-polar molecules. Then in the second step, for a moment, the electrons are pushed over to one side, so it's delta minus, the other side is delta plus. So the second molecule lines up so that opposites attract. So we have the delta minus of the first molecule connecting to the delta plus of the second molecule, and there's an attraction represented by that white line for a moment. It's very temporary. And then the electrons go back to being normal and the force goes away, and we have our bottom step where we're back to 2 non-polar molecules. So non-polar and temporary, again, are key words for London dispersion force. The second force is dipole-dipole forces. This exists between polar molecules, and it's permanent. So the key words here are polar and permanent. So we're talking about molecules that always have a little bit minus and a little bit plus ends. They're always like that. Okay, so they always have a little bit minus and a little bit plus, like HCl, which you can see there. The H is a little bit positive, the Cl is a little bit negative. That's because Cl is closer to fluorine, so it wins that tug of war of electrons. So the electrons are pulled towards Cl, electrons are negative, so Cl is delta negative. Now, as we have another molecule coming close, how is it going to line up? Well, it'll line up like this, so that the delta positive of one molecule is close to the delta minus in the other molecule. So we have an attraction here between these two atoms, or molecules. We have an attraction between these molecules. So opposites attract, and they are going to be close to each other. We won't be like this orientation. That's wrong. We're going to have this orientation. So they'll kind of bobble around each other. And you often see dipole-dipole forces in liquids, and they kind of flow around each other, keeping this delta minus to delta plus sides close to each other. So again, in the picture with the HCl, we see the white dashed line between the delta minus of the first molecule to the delta plus of the second molecule. Again, opposites attract. And now dipole-dipole is permanent, and you have to have polar molecules for dipole-dipole forces. So again, this is stronger than London dispersion forces, and we have to have polar molecules for dipole-dipole. Dipole just means two poles. So each molecule has two poles, a plus and a minus pole. So dipole-dipole, two polar molecules for this force. Great, let's move on to the third force. This is stronger still, the hydrogen bonding force. This is an especially strong dipole-dipole force between molecules that contain a very, very polar H to F, or H to O, or H to N bonds. So it's H to NOF, N-O-F, NOF. You have to have a hydrogen bonded to an N or O or F in the molecule to have a hydrogen bonding force. So if we look at the picture of the water molecule, we can see hydrogens are a little bit plus, oxygens are a little minus. Now I have two water molecules in that first drawing, and I have a dashed black line between the O of the first molecule and an H of the second molecule. So this is how a hydrogen bonding force looks. The little bit positive H of one molecule is attracted to the little bit minus N or O or F atom in the other second molecule. So it makes a hydrogen bond. It's not really a bond, it's a force, right? So that's why some people call this hydrogen bridge, because it looks like a bridge from the H to the N or O or F of a second molecule. So that's where hydrogen bridging comes from, but we'll call it hydrogen bonding today. But it's not a bond. Remember, it's not a bond. Now the second picture here is pretty with the red oxygen atoms and the white hydrogen atoms, and you can see the hydrogen bonding forces with the dotted black lines. And it's always a positive H to a negative O, a positive H to a negative O, a positive H to a negative O, a positive H to a negative O. It's never H to H or O to O, because opposites attract. So it has to be a positive H in one molecule to the negative O in another molecule. Opposites attract. So the hydrogen bonding force is always from an H to an N or O or F of a second molecule. So again, this is stronger than dipole-dipole force, but it's still much weaker than a bond, a real bond, an ionic or covalent bond. Remember, hydrogen bonding force is not a bond, it's a force. And this is the same picture that was on the previous slide, again showing the hydrogen bonding forces in this group of water molecules. Okay, so this is the third strongest force. And this brings us to our last and final force, a fourth force, the strongest one yet, ion dipole force. Now this occurs between a polar molecule and a fully charged ion. This is the strongest force. So what happens is we have the negative charge on the water molecules, which is the oxygens, which are in red, are attracted in the picture to the fully charged positive sodium ion Na+. So sodium is a complete +1. Now the waters are just a little bit plus and minus. The oxygens are the little bit minus. And so they all point in towards the sodium because opposites attract. So you can see we have 6 water molecules surrounding that sodium ion. So we have 6 ion dipole forces in that picture. So the little bit negative oxygens point inwards towards the positive sodium. So we have an ion and we have polar molecules, ion dipole force. Now let's show, again, sodium chloride, NaCl. It dissolves in water. When it does that, again, the sodiums here up on top have the oxygens pointing in. We just saw that on the previous slide. And now in the bottom picture here, we have the Cl minuses. What's going to point in towards the Cl minus ion? Yeah, not the O's in water, but the H's in water, because the H's are a little bit positive. So all the little positive hydrogens are going to point inwards towards that Cl minus because opposites attract. And you can see in the picture here, we have hydrogens pointing inwards. We have 1, 2, 3, 4, 5, 6, 7 water molecules around that Cl minus, and opposites are attracting. So for ion dipole force, again, you have to have an ion and it's surrounded by polar molecules. It's surrounded by polar molecules. All right, we're going to stop here for this second video, and we're going to come back and I'm going to ask you some questions about the 4 forces. So good luck, GCC. Bye-bye.